Start the recording. All right. Hello, everyone, again. I just started the recording. I've been talking. But as mentioned, we're going to be going over chapter 12. For those of you that'll be watching the video, uh, right, coming in and watching the video. So we should cover all of chapter 12 today. If we don't, obviously, we'll pick it up on Thursday. And then after today, we have one more chapter to cover. And we will not have homework on that chapter. On chapter 13, there will be no homework assignment. So this will be the assignment for this week. Will be your last homework assignment. Woohoo! I know you all are excited about that. I did the woohoo for you all. So anywho, let's jump into it. What we're going to be covering, things we're going to cover. We're going to try to talk a little bit about electric current, voltage. There you go, Lawson. Electric power, electrical circuits. Going to talk a little bit about batteries. Also a little bit about AC and DC. And so, well, I'll let the video do the talking on that. So let's jump into it. Electric current, voltage, and electric power. Electric current. All right, this is probably one of the most interesting subjects because if you're a mechanical engineer or aspiring mechanical engineer or an aspiring electrical engineer, the aspiring electricals will be very familiar with this. Mechanicals probably not so much, but you will see a lot of correlations, right? So when you think about electric current, the flow of electricity, when you think about current, it's a flow, so it has a rate, right? And so just like when you think about a fluid, right? Fluid meaning liquid or gas, right? It flows, so it has a rate. And so I always like to talk to my students. I always tell them, like, when you think about something that flows, it's like you think about a fluid, you think about current, and they flow similarly. Then you have, when it comes to um, a fluid, like gas or liquid, and you have a circuit, right, or a pressure system, right, you're going to have some type of resistor. You're going to have some type of energy source, right? Whether that be something flowing in at a certain pressure, or the fluid flowing in at a certain pressure, or the fluid flowing in at a certain velocity. You're going to have some sort of power source, in other words, right? And then you're going to have some type of resistor, right? In a mechanical system. And that resistor could be an orifice. And what that orifice does, or like the product that I designed with my company, is a choke, right? And so what does that choke do? That choke, it chokes the flow. It resists the flow. So it reduces the flow so that you can reduce the pressure, right? Just like in an electrical circuit, right? You have a resistor to reduce the voltage, right? To slow down the current, right? And so, anywho, just a little comparative speaking for you guys that are mechanical and electrical, just to show the similarities and how they both work when you're looking at circuits, right? Mechanical and electrical circuits. But anywho, electrical current as a fundamental dimension. We're going to discuss voltage, but let's jump into electrical current. Electrical current is merely measured by ampere. That is the unit of measurement. But it is constant current, which, if maintained in two straight parallel conductors of infinite length, of negligible circular cross section, right? Negligible meaning the infinite uh, parallel conductors. They're assuming like wire, such as wire, right? And I'll draw it out for you. But anywho, current, constant current, which if maintained in two straight parallel conductors of infinite length of negligible circular cross section and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the minus 7 Newton meters of length. What does that all mean? Well, I like to draw it out. And for all of you that have had circuits, remember this is intro to engineering, so don't be too hard on me if it looks funny. So if you have two infinite single conductors parallel, they're parallel, right? and they're at a distance of 1 meter apart. Right? And you have some constant current flowing through these conductors. Right? It will produce some sort of a magnetic flux, right? And it sort of like spirals, is what it does, right? And so, well, that will produce a force between the two. What is that? Was it 2 times 10 to the minus 7? I can't even remember. 2 times, that's ugly. That's horrible. People watching this are like, what is he doing? Draw 2 times 10 to the minus 7, I believe. I think that's it. Let me grab my book. Chapter 12. It produces, 2 times 10 to the minus 7. Where's my thingy? Newtons. It's like a flux of 2 times 10 to the minus 7 Newton meters. All right. Well, they say a force, but it's like a magnetic flux or something like that. But what is the importance of this all? Right, when you have current flowing through these airless, negligible air conductors or wire, right? What's important about this when you're running that current through it, if I can't remember exactly, I'm gonna have to Google it. I'm gonna have to look it up. I can't remember. I should have looked it up before I came. But I think if the currents are running in the same direction, they will oppose one another. But if the currents are running in opposite direction, they will attract one another. So don't quote me on it. I'll have to look it up. I think that's how it goes. But anyways, back to the lecture at hand. If I could find it. I think that's it. Yeah, that's it. All right. So that's basically what that's saying, that statement is saying. So unlike charges attract each other while like charges repel. So there you go. I think I quoted that correctly. Then you have the unit of charge, which is a coulomb, and 1 coulomb is equal to the amount of charge that passes a point in the wire in 1 second when a current of 1 ampere is flowing through the wire. 1 coulomb. I know that's all like, what? It's funny because 1 coulomb is basically 1 second of a current, right? When a wire, 1 coulomb, the amount of a charge that passes a point in a wire in 1 second when a current of 1 ampere is flowing through the wire. And what you're going to learn is they're all reciprocals of one another. They are basically the same. They all equal one another when you're looking at a coulomb and an ampere passing through a wire. All right. Then you have the electrical force. It's going to get fun here in about 4 more slides. Trust me. But anywho, I'm just reading through this because a lot of this is just informal. You have the slides. Yes, I do know. You can read them yourself. Yes, I do know. But I want to read through them anyway. So just as we go through this, if you have questions, just go ahead. Feel free to ask. But then you have the electrical force. The electrical force is exerted by 1 point charge on another, right? And that is proportional to the magnitude of each charge, inversely proportional to the square of the distance between the point charges. What does that mean? It basically means this. That's simply what it means. These, the Q1 and 2, those are the charges, right? And then the square of the R is the distance between those 2 points. If you go back to my handy, which I know I don't have my drawing up, but if you imagine those two parallel wires or lines that I drew, and then they're looking at the electric force between those 2 points on those 2 wires. And this is how you would basically calculate that force, where K is a constant of 8.99 times 10 to the 9th, right? Coulomb, and then per charge, sorry, squared. And then you have the charges between each of the wires. Sorry, I'm hungry. Everything's moving a little slow. My food is in there. I didn't get a chance to eat it. So yeah. Anywho, yeah, it's not your problem. It's mine. But it's the multiple of the two charges going through both of the wires, right? Times the constant K divided by the distance squared, and that's how you would solve for that force. All right. So that's all that's saying. That paragraph above is saying. An electric charge, whenever there exists a difference in electric potential between two bodies, you will get an electric charge. An electric charge will flow, and this is, remember this, an electric charge will flow from the higher electric potential to the lower potential region. What does that sound like? It sounds like heat transfer, right? Where you have the higher, the temperature, the element or object with a higher temperature will always, a region will always flow from high to a lower temperature region. So you think about here again, flowing of a fluid, flowing of electricity, right? The flow of charge will occur when two bodies are connected by an electrical conductor, such as copper wire. And then another thing, right? You think about, I know I'm doing a comparison because I just want to, like, for those of us that are mechanicals, to help you make sense of the electrical charge. And so when it reads something like the flow of charge will occur when two bodies are connected by an electrical conductor, right? You think about in heat transfer, you think about the thermal conductivity, right? For something with a high thermal conductivity, right, like such as glass, right, you will be able to pass heat through it at a greater rate, right, at a great heat transfer rate, such as electricity, right? Copper wire, it has a high electrical conductivity. So when you're passing electricity through it, you're going to get a lot of electricity flowing, right? So just think of it in that way, in terms of that. I know it may sound confusing, sort of, but if you think about heat transfer and how we were discussing thermal conductivity and how heat passes through a glass, because glass has a high thermal conductivity, and basically it has a low resistivity, right? The resistance of glass to heat is very low. So it'll just allow heat to pass through it at a high rate, just like aluminum foil, right? If you want to heat up something quickly, get some aluminum foil or get some glass, right? So if you want to get a charge on something very fast, so you're going to use copper wire because it has a high electrical conductor. It's a high electrical conductor. All right. Any questions on that? No, maybe. All right. So electric current. All right. Electric current. Good deal. The flow of charges measured in amperes, which we discussed that. You know what I mean? Electric current is measured in a unit of amperes. Then voltage, volts, obviously you all should know that. And then you have electromotive force, EMF, which we won't really go into much of that in this class. But when you get in your circuits class, you will definitely go over EMF. All right. But just want to give you some defining terms. You don't have to worry about it. It won't be on the test. But then you have direct current, right? You have direct current, and then you have alternating current, AC and DC. So most of you should know direct current, flow of electricity that occurs in one direction, right? And then alternating current, it flows back and forth. So you think about a power grid, it flows back, right? So if you're losing electricity in your apartment, it's coming from a power grid, basically power plant. So when you cut it off, it flows back to the power plant. Direct current, it only goes one way. So it's only out, right? It's only out. And so you could definitely use direct current on your house, at your house, right? It would take a lot more, not necessarily a lot more. It would cost a lot more to get a power source to supply power to your apartment or your house directly. And then you would have to recharge that thing some kind of way. But with that being said, let's go to the video. I looked at a little bit of it. I hope this guy's funnier than I am, so he keep you guys from falling asleep. You know, I do my best to keep y'all from falling asleep, but it doesn't always work. Oh.
So you won't miss any future videos. Electricity seems pretty straightforward, right? You plug your gadget into the wall and the electrons flow through the cord into your device, which lights up, produces noise, or makes a feeble attempt to keep you company. But as it turns out, there's a lot going on behind the scenes when it comes to power delivery. And in fact, most digital electronics like computers, TVs, and game consoles cannot directly use the alternating current or AC power coming out of your outlets without converting it first to direct current or DC. So why is this the case? Well, the problem is that alternating current is basically what it sounds like. It's when the electrical current changes direction many times per second. By contrast, the more straightforward direct current has electricity always flowing in the same direction. So why then is power transmission from an electrical plant to your house done with AC? Well, the answer lies in how easy it is to change voltages within an AC system. You see, when an electrical plant spits out power, the voltage is stepped up to hundreds of thousands of volts. This is because high voltage electricity is more efficient to send over long distances. It helps prevent power loss. But before it reaches your home, a series of transformers is needed to lower that voltage down to a safe level so that you won't get fried every time you try to plug something in. So that's 110 volts if you're in North America, or 220 if you're over in Europe. Now, because AC power is changing direction all the time, this creates a changing magnetic field inside the transformer that induces a current and allows the transformer to work. In a DC system, the current is traveling in the same direction all the time. So those simple, inexpensive transformers that you see in AC systems simply won't function. This is part of the reason that AC became the dominant method of power transmission a long time ago and remains so to this day. Now, thanks to some more recent advancements in technology, high voltage DC transmission systems do exist, especially for connecting different AC grids to each other. But alternating current remains by far the most common way that you and I get power delivered to our homes. This brings us back to our electronics, which you might remember can't use AC and need DC power. Now, if you've ever built a computer, you might already know that the primary function of a power supply is to convert the AC power from your wall into clean, usable DC power for your system's components. Electronics need DC power because the tiny components that make them up, such as the all-important transistor, are designed and built with a specific polarity. That is, they're designed to work with electrical current that only flows in one direction, so that things like logic gates can function in a coherent fashion. Constantly switching the current flow would totally disrupt the internal logic and leave you with basically a paperweight. Like it'd be like trying to go from the bottom to the top of the water slide. You'd ultimately be putting in a lot of effort and for zero thrills. AC power also gets interrupted briefly every time it switches direction. You can see this if you've ever watched a high-speed video of an incandescent light bulb connected to a regular old AC lamp. So it'll flicker many times per second according to how often the current changes direction. So that's 60 times in North America and 50 over in Europe. Now this is fine for a light bulb under normal conditions, as your eyes probably won't even notice this sort of flicker. But sensitive electronics need a constant supply of power and won't take kindly to small interruptions, as their internal logic depends heavily on maintaining very specific voltages, which you can't realistically do with AC. So this is why so many of your electronics have that boxy AC to DC adapter instead of just a plain old wall plug, because you need extra hardware for the conversion. I mean, even guitar amps have to convert AC into DC. In fact, I heard that one metal band from Australia found the topic so fascinating that they actually named themselves after it. What are they called again? Wolfmother? Pendulum? Yeah, I can't quite remember. I do think they made it pretty big, though. Speaking of AC/DC, are you in the market for a new power supply? Well, why not check out our sponsor, Seasonic. Their prime titanium fanless 600 watt is not only rated for 80 plus titanium efficiency, the highest 80 plus rating, but it's also the highest power fanless unit on the market. So you can power a high-end gaming rig with whisper quiet operation from your PSU. And of course, you'll be getting Seasonic's legendary build quality, including gold-plated high
Man, thanks. I was just sitting here talking away. Oh man, thanks, honey. But anywho, as I was saying, I hope that made sense to you all. Yeah, man, I was just going. And but yeah, hope that made sense. You know, the guy was sitting there trying to advertise a power supply to us, and you know, maybe you guys want that for your guitar, or I mean, you know, our gaming system that you're building. But that's not why I shared that video. I shared that because just trying to give you some clarity on AC/DC. And as I was saying to myself just now, there are some systems out there that do supply direct current in some fashion to homes. Not sure what capacity. Hadn't done any research on it, but I know there's capabilities of it. But supplying direct current to a home would be very inefficient, just because of the distance, as he so eloquently pointed out, right? So that's why you have the alternating current flowing to your homes, because it's so much more efficient, and you can get so many more voltage. You can get so much more voltage to your home using alternating current. All right. Now let's talk about some stuff that is going to be relevant to you, such as Kirchhoff's current law. All right. And that just simply says current flowing into the node is equal to the current flowing out of the node. All right. So when you're looking at solving a problem, when you're looking at solving some type of a circuit, especially when you get in the circuits class. Always remember the current flowing into the node. You're going to use Kirchhoff's current law quite a bit. Current flowing into the node is equal to the current flowing out of the node. All right. So you have an electrical circuit, which brings us to some problems. An electrical circuit is just a combination of various electrical components that are connected together, right? You have your wires, your switches, your outlets, resistors, capacitors. You have transistors. What else you got? You may have some cases you'll have a power supply. You have various different electronics making up this circuit. But in this course, all you're going to see are wires. You're going to see a voltage, which would be your power supply. You won't see any switches, but you'll just see voltage, wires, and resistors. All right. So resistivity values usually measured using samples made of a 1 centimeter cube or a cylinder having a diameter of 1 mil, right? And those are like copper wires or even sometimes alloy metal wires, right? You'll see them measured in mil. In length in feet, obviously in imperial. They'll probably more than likely be, they won't be in feet, in SI units. So let's get up to Ohm's law. And you should know this, 1 voltage is equal to resistance times current, all right? Voltage is equal to resistance times current. And then I'm gonna do, and then you know power is equal to voltage times current. So I want to talk about this sort of a circuit, a series circuit, right? The series circuit. For a circuit that has elements in series and arrangement, the following is true. The voltage drop across each element can be determined using Ohm's law. All right, that holds true. Also, the sum of the voltage drop across each element is equal to the total voltage supplied to the circuit. All right, so that basically means across each resistor, the current across each resistor should total up to be the supplied voltage. So if you came in with 9 volts, the volts across each resistor will equal total, when you add them all up, it's going to equal 9 volts. All right, in a series. When a resistor is in a series, okay? So the total resistance is the sum of the resistance in the current. All right, so that's when you're solving the resistance. So the total resistance is the sum of the resistance in the current. That means if you have multiple resistors, right, the total resistance is the sum of each of those resistors. So if you're trying to choke this current, I was going to say flow, trying to choke the flow of this current, put in more resistors in a series, right? And you're going to reduce that voltage going throughout that circuit, right? And so when I ask, well, what's the total resistance? Well, you'll just say, oh, it's R1, the sum of R1 through R5 if you had 5 resistors. All right, so that's how you would get the total resistance. Does that make sense? Yes, no, maybe. All right, well, let's work an example. And I'll show you what that looks like. It looks like this. See, this is a series circuit. They all share the same current. They all share the same current. All right. So let's work an example. Let's find one first. Find a good one. Yeah, here's a good one. Let's look at example 12.4. Example 12.4. All right. 9 volts. So 9 must be popular with voltage. 9 volts. All right. They have light bulbs. We're just gonna put little resistors here. Okay, so I drew this out. What you have here, you have 9 volts coming into this circuit. All right, R1 is equal to 3 ohms, and that's another thing that I didn't say. Ohms are the units for resistors. All right, it's 3 ohms, R2 is 7 ohms, and then R3 is 9 ohms. So if I were to ask you, well, what is the current? What is I equal to for this particular circuit? All right. And then I'll say, well, what is your total resistance? What is that equal to? All right. So you guys would say what would you guys say if I asked that question? What is R total? All right. So R total is 19. So what is the current for this circuit equal to? And if you all didn't remember, what is Ohm's law? What is Ohm's law? And that's how V is equal to IR. Thanks, Hunter. So V is equal to the current times the resistance. So then to solve for I, you would basically divide voltage by the total resistance. All right, so then I would equal what? I would be 9 divided by 19. Absolutely. All right, so good deal. So then if we were to add more resistors, let's do another one, positive to negative, and that's another thing. So the voltage always flows from the positive to the negative, right? So you got 1, you got 2, you got 3. Wait, it looks horrible. Let's redo that. All right, that's 1. Then you had 2. You have 3. You got 4. You get 1 more here. And then bam. And then you got 1, 2, 3, 4, 5. And you got R1. R2. Wait. R3. R4. And R5. You say we have 9 volts. And then let's say our I, let's say is equal to 5. Ha! This is an interesting one. So how would you solve for your R here, right? It would be obviously easy, right? Because all you would do, you would say V is equal to I R total. You would divide by I to get your RT, right? Simple as that. But then if I were to say, well, what's R1? Now that'll be a little bit more difficult to solve, right? Because you got 1, 2, 3, 4, 5 unknowns, and you only have 2 equations. Well, you really only have 1, but you do know the I into the node, which you can use Kirchhoff's law, but you don't really have any nodes, so that would be difficult, right? So you would need more information. That makes sense? So you will not see a problem like this, right? But I could give you a problem with nodes, right? Right, and then I could make you solve. You can't. No, y'all are funny, right? I'm just saying, right? I could give you that, right? I could give you a problem like that, and I can make you guys solve for the individual resistors. Right, I could do that. So just be prepared. Right. So I can do that. And just remember, I would obviously have to tell you the current flowing into the node and the current flowing out of the node. Right. But what you do know is the current flowing in sorry. What you do know is the current flowing in is equal to the current flowing out. Right? So you know I1, if this was I1, and this was I4, this was I2, you can say I know I1 is equal to I2 plus I4. Right? And so I could do that. But first we would need to go over this because this is a circuit in parallel, right? It's not series. And so how do we solve a circuit that is in series? Well, let's talk about that. All right. Let's talk about it before we jump into it. But I'm just pointing out what I could do. Not saying I am going to do it, but I can do it. And I haven't decided if I am going to do it yet. But food for thought, just something to think about, something to prepare yourselves for. All right, so a parallel circuit. In a parallel circuit, components are connected in a parallel arrangement. Okay? The electric current is divided among each branch. The electric potential or the voltage across each branch is the same. Get that? The electrical potential or voltage across each branch is the same. Okay? So where I showed you R1, I showed you R4, that was like one branch, right? Then you had R2, and then you had, what was that? R3, and I believe R4? Can't remember. Maybe no, R5. Maybe that was R5 at the bottom. Can't remember exactly. I know y'all probably can't remember. But those are different branches, right? So going into that node and coming out of that node, and then you have basically I1 and I4 would be the same branch where I drew the current. So the voltage within that branch would be the same for both of those resistors. All right, so you can solve that branch. Okay, so then if the sum of the current in each branch is equal to the total current flowing into the circuit. All right, the sum of the current in each branch. So just like the resistors, where you totaled all of the resistances, right? And then that would be R total. So the sum of the current in each branch is equal to the total current flowing in the circuit. So, all right, does that make sense? And the current flow in each branch can be determined using Ohm's law. All right, so you can use Ohm's law for each branch, right? As well as determining currents you don't know, you can use Kirchhoff's law by showing what current flowing into the node is equal to the current flowing out of the node. So let's look at that circuit. So this is a circuit in parallel. All of the resistors are parallel to one another. Now, this is where it gets tricky, because if I ask you what R total is the reciprocal of R total is equal to, or 1 over R total, is equal to 1 over each of the resistances within that circuit. So where a lot of times people make mistakes, they will say R total is equal to 1 over R1 plus R, is equal to 1 over the sum of R1 through R5, right? And that's not correct. You would have to say 1 over R total is equal to the sum of 1 over R1 through R5. All right, so keep that in mind. Now, let's solve this. Let's work an example. And we'll just do example 12.5. All right, just keep it easy. All right, cool. So you got 9 volts again. I'm telling you, something about 9 volts. All right. And we will put resistors instead of light bulbs. All right, and then, and so R1 is equal to 3 ohms. R2, 7 ohms. And then R3 is equal to 9 ohms. All right, so what do we need to do to solve this problem? What is R total? What is I? We know V is equal to 9. So what is R total? What is the total current? So we would start out saying 1 over R total. Is equal to 1 over 3 plus, there you go, Z, get ahead of me, 1 over 7 plus 1 over 9. And so what do we need to do to solve the problem, though? A lot of times, because you're going to have to show your work whenever you work this out on the final exam. So what do we need to do here? what do we need to do with all of these fractions? There's a term. It's two terms that I'm looking for. I think it has a total of 4 syllables. No, 5. Well, I guess it's 7. 7 out of the terms collectively. There it is. Common denominator. Common denominator. All right. And so you obviously, to get 9, you would go 3 times 3, but we got that 7 there, and that's what throws a little monkey wrench in the plan. So Patrick says, Condor says 63. So 7 goes into 63. How many times? 9 times. There it is. All right. And so obviously 3 would go in there 21 times. All right. So let's do it. We got 1 over RT would equal 21. Go ahead, Austin. What do you got?
Can't you also do 28? Or no?
3 go into 28?
Yeah.
How many times does 3 go into 28?
Oh, wait, my bad.
Right. 9 doesn't go into 28 either. So we got to use 63. So to get to 63, you multiply 21 times 1. And I'm going to write this out like we're back in grade school math. So we can see it. 21 times 3 plus 9 times 1 over 9 times 7, and then plus 7 times 1 over 7 times 9. That 9 looks bad. I know it does. Let me fix it. All right, so we got this 9. All right, and voila. And so it equals 21 plus 9 plus 7 all over 63. There it is. There you go, guys. So 37 over 63 is equal to 1 over R total. All right. So R total will be the reciprocal. So I'm going to move up here. R total is equal to what? 63 over 73. What's our decimal answer? Did everybody get 1.7? Should have. It's pretty simple to just type that into your calculator. All right, so then, now what is I? I. So we know V is equal to IR. All right, so what is I? We just divide the voltage by the resistance, and we should get 9. We should get 9 divided by 1.7. What is our answer? And we got 5.285. I'm going fast. I'm trying to write this fast. So that's why it's looking bad. Rush through it. 5.285. All right, amperes. Okay. Any questions? All right, good deal. Good deal. Easy peasy, right? Now y'all know. Y'all know I like to mix it up. So let's mix it up. Okay? Let's work another example. Let's say we had something like this. We got 9 volts, right? Got 9 volts. We got a resistor here. We got a resistor here. We have another resistor here. And another resistor here. The plot thickens. All right. We got this resistor is equal to 2 ohms. Let's mix it up. This resistor is equal to 3 ohms. This resistor is equal to 5 ohms. And this resistor is 6 ohms. All righty. What do we need to do to solve this problem? What is our total? What is our total? What is I? What do we need to do to solve this problem? So Hunter says 2 plus 1 over 3 plus 1 over 5 plus 1 over 6. Is that correct? 1 over 2? So in this case, you're going to have to break it up. All right. So as you can see, this part is what? This part is in, what are all 3 of these? RT. All 3 of these resistors are in parallel. So for this section, what you would have to do is you would go 1 over R total is equal to 1/3 plus 1/5 plus 1/6. All right. And so what do all of these have in common? 30. All right. So then we would find that common denominator. And this time I won't write it out. Skip some steps.
Down here.
We know to get 30 from 3, got to multiply times 10. So we have 10 over 30.
Put hands on my boy. See you in the talk. Sure.
Plus 6 over 30. Plus 5 over 30. All right. And so then you have all of that equal to 21 over 30. 1 over RT. So RT would be equal to 10 over 7. All right. So then what do you do? Well, to get RT, so if you make this R little t, to get R big T, now you make, because once you put it all together, now rewrite this. You rewrite this circuit, it'll be in series now. So R little t would be 10 over 7. And then R1 would be 2. And so then it would be 2 plus 10 over 7. So the way you were doing it, Hunter, you would have missed it because it would be the reciprocal of 1 over RT. Then you would have to, once you solve for that reciprocal, the inverted 1 over RT, which would be RT after you solved all of the common denominators, you end up with 10 over 7 versus 2 plus 21 over 30, right? So that would be incorrect. So it would be actually 14 over 7 plus 10 over 7, 24 over 7. And that would be your R total. Oh, let me write it up here. So if you come up here and you find your common denominator, obviously it's 7, so it would be 14 over 7. And so 14 over 7 plus 10 over 7 is 24 over 7. So RT is equal to 24 over 7. All right, and then I is equal to V over R. All right. And so you would just plug in your 24 over 7, 9. So it would be 9 times 7, 63, 63 over 24. That would be your I. And you can reduce it, right? Because 3 goes into 63, 3 goes into 24. So, all right. So it'll be what, 21/8 or something like that will be your answer for I. Is that correct? Anybody checking my work? (21/8) for I. He said, I believe in you. All right, good deal. So, what else we got? Let's see. I think that might be a good stopping point. All right, so parallel, then you have capacitors. Yeah, that's a good stopping point. We'll pick up with capacitors on Thursday. All right. Sounds good. I know you all were ready to stop. Cool. Well, you all enjoy your evening. Oh, absolutely. So, everyone enjoy your evening, and we will talk to you on Thursday. Thank you. Have a great night. Have a